Okay, welcome to our curriculum inspiration, looking at engaging ways to introduce students to parabolas. So, the activity introducing parabolas should be the start of every student's journey into exploring this truly amazing curve. The focus in most textbooks, and indeed the Australian curriculum, is not actually the focus. Apologies for starting with such a conundrum, but most courses seem to start with generating tables of values, followed soon after by quadratic algebra, where students spend most of their time expanding and factorising equations. Parabolas are usually the first nonlinear function that students encounter, but for many students, a parabola is simply a U-shaped curve. Focus and directrix are not mentioned in the Australian curriculum and often not mentioned in the classroom. However, they are fundamental to the construction of a parabola and in understanding its physical attributes and its many applications. The terms focus and directrix shouldn't be left just for analytic geometry. These terms are simple and easy for students to understand, as you'll see as we work through this activity. The teacher notes provide some documentation and materials to launch the activity. The teacher notes start with a paper folding task similar to the one that you can see on your screen right now. That links you off to a TI Nspire file, which I'm going to use to demonstrate the whole paper folding idea. Now, if you're doing this with students, obviously, they would have an A4 piece of paper in front of them, and they fold the bottom edge of the page up to a point somewhere on the page, which coincidentally we'll call point F. They repeatedly fold the page so that the bottom of the page continues to touch that one point. Now, when the students are creating those folds, they can use a ruler and a pen to create a line through that crease. Let's see what that looks like after they've done it a few times. And there we have an envelope, which we'll call a parabola. We haven't proven that it's a parabola. It's a U-shaped curve at this particular point in time. The advantage of doing this dynamically is that you can actually start exploring some of the different shapes that you can get if you'd put the original point in a different spot. So we'll move on to the next one in the teacher's notes. Let me show you what the teacher presentation file looks like. So you can see this one's designed to work on the handheld, same as my big diagram. And we see a little one of those curves, little baby one. The next section is we get students to do, in the teacher notes, a physical activity. That is, we get the students to line up across the back wall of the classroom and we ask them to walk towards an object that the teacher places, let's say, somewhere in the middle of the room. The instruction is essentially the students walk perpendicular to the wall and they stop as soon as they are the same distance from the wall as they are from the object. And if students are doing that reasonably accurately, it will form a curve. This time we're actually moving towards what we now know is a parabola. That is a set of points that are equidistant from a line and a point. The line is called the directrix and the point is called our focus. Once we've done that, we can then help students understand this idea of a locus, that is a set of points that have been given a rule, and we can move this little segment and see that we can form a couple of triangles. Our first one is going from our directrix, or in this case our x-axis, or in a classroom, the back wall, up to our curve. The other line goes to the object or focal point. Then if we draw a line from where the student would have been standing at the back wall directly to our object, we can see, dropping a perpendicular line between those two, we can break that triangle that we've formed into two congruent triangles. Now, the next part, and again, this is still in the teacher notes, we can see that the curve that's formed, this locus, is actually a parabola. And as we generate values, and you can specify specific values, we can test to see if these values sit on a specific curve. In this case, I've set the directrix up at -1/4 and the focus at 1/4. That's the one that actually gives us the parabola of y equals x squared. We can then, of course, move these points around to see different shape curves. I'm just going to drop another graph page in here just to give you an idea how easy it is to put the focus and directrix in on any parabola. I'll type in y equals x squared, then under Menu, Analyze, and these things are called conic sections, which we'll get to shortly. And you can see here we can access focus and directrix. So there's our focal point. I can go back through Menu, Analyze, Analyze Conic, and select Directrix. Oops. And there's our directrix. These things are live, so if you change your parabola, the focal point and the directrix will change accordingly. And that every single point on this curve is the same distance from this dot, the focus, as it is from our directrix. So we've gone beyond just being a U-shaped curve. Just returning back to here, we've got some animations here as well, or some things to reveal, so you can show and hide various aspects to help students understand what's going on, and to help them understand what a conic section looks like. Obviously, it'd be much better if you had a cone and just started cutting it, but I've created a virtual one here so that you can have a look at the cross-section and see that it's creating this so-called U-shaped curve. Now, I have another one. This one isn't included in the online activity, but I will certainly make it available to those people that would like to have a copy of it. You've probably seen this dish before. It was the star of a particular movie and very relevant at this particular point in time since we're at the anniversary of the landing on the moon. And what we have is a set of points that I'm saying is an electromagnetic wave. So in other words, a wave that's come from outer space, a signal. Students may question why it's a straight line. Well, essentially, if you keep on extending a curve, that is a circle, and you get further and further away from the center, a segment of that curve looks a lot like a straight line. So as you can imagine, if that curve originated, that sound wave originated, let's say from the moon, or the electromagnetic wave originated from the moon, it's going to be pretty straight, that little segment that hits the dish. And then as time goes on, it gets closer and closer to our dish. And then as the wave hits the dish, it bounces off our curve. And heads towards one point, our focal point. Now, there's a few things, and what's really important, we often tell students, oh yes, the sound wave or the electromagnetic wave or the light is reflected back through the focus. But there's a really significant part that the kids don't get if we don't go through some of these aspects or properties of a parabola. I'm going to rewind a little bit and let's have a look at just one point. This point over here is now heading back towards the focal point. If it had continued in its current or its previous state, it would have been heading straight down, let's say, towards the ground. Now, the time it takes to get to the focal point has to be exactly the same as any point that was on that original wave. And the only way students can understand that is to go back and have a look at the original geometry back in our teacher notes, where, let's say, point P was on that curve. We know it's got the same distance to bounce off here as what it would to go back through the focal point, because those distances are the same. And if the point had been further over, it would still be that distance away. And by the time it gets to here, it would have been the same amount of time as it would to get to here. So all points that are on that straight line hit the focal point at the same time. And that's critical, because otherwise our sound or electromagnetic wave or image would be distorted. Now, another really good video I'd suggest people have a look at. This one's from YouTube, and it's by a person called, well, he calls himself the Mathologger or Mathologger, and his actual name is Burkhard Polster. So I'd recommend everybody jump on after this webinar and have a look for the Mathologger, and his video on this particular occasion is called Illusions or Parabolic Illusions, and he goes through some similar things here. He goes a bit deeper into the geometry, and he'll show you more detail on why those sound waves are not distorted when they hit. Now, a quick and final look at what the activity looks like. You can see we've got a picture of the telescope at Parkes. Here's some of the teacher notes, so everything that we've been going through. Our class locus, that is getting the students to walk from the back wall of the classroom. The creation of an envelope. Kids enjoy the dynamic nature of that with all the instructions there. They construct a locus, so they're learning some good geometry terms. And the last bit, one little application, and that is, and this is using the actual dimensions of the telescope at Parkes. It has a diameter of approximately 64 metres, and the radio waves that bounce off that surface head back towards a focal point 27 metres away. So we could see, we could effectively define the curve. But if we imagine that all of those waves were focused into a region just 10 centimetres squared in size, that's pretty small. The magnification, that is the change in intensity of that wave, is approximately 3 million times stronger than what it hit the dish at. And that's how we can see so far out into space with these telescopes, because we can amplify signals by more than 3 million times. Now, if your kids aren't impressed with that, I don't know what we can do to get them interested in parabolas. Certainly got to be better than spending a whole term factorising. Okay, that's about all we've got time for. We try and keep these sessions short and sharp. If you have any questions, please be happy to stay on and we can answer those questions for you, or catch us on our next curriculum inspiration or webinar. You'll find lots of links on our website. Thanks for watching.